hey, you want to get together and watch Mr. Sanders' movie? That'd be hilarious. Okay, polyprotic acids. First, I want to talk about polyprotic acids. This isn't going to take very long. And then I'm going to talk about weak bases. But just like, even strong acids and strong bases, just like we've got this pH-POH relationship that is kind of the same but opposite. I think you know what I'm talking about. It's going to be exactly the same for our weak bases. We're going to have a very similar equation that's going to be the same but base opposite. So really, when we get to weak bases, we're not really going to learn anything new. We just need to flip it into the base language and then turn it back into a pH. So today's lesson is really pretty straightforward. So first we're going to talk about polyprotic acids. These are acids that contain more than one H, things like sulfuric acid, H2SO4, phosphoric acid, H3PO4. And what do we do with these multiple H's? At this point, I've told you, only worry about one H falling off at a time, and that's still true. But what I want to talk about now is, let's think a little bit about those second and third H's, and then we'll talk about how we can think about it. But still, what I said is true. Deal with only one H at a time. You never remove a bunch of H's, all right? Now, if you're doing a titration equation where you've got a strong base up against a polyprotic acid, like sodium hydroxide, that strong base will rip off all three H's, okay? So if you were to do a titration, phosphoric acid up against sodium hydroxide, those hydroxides will rip off all three H's. But that's different than this scenario. The scenario I'm talking about is putting something like phosphoric acid simply into the water and letting the H's fall off, all right? H's falling off and making a solution acidic is a different reaction than the H's being ripped off by a base, OH, as it turns into water. So what I want you to take out of that last little conversation is, when we talk about polyprotic acids in pure water, and we're just letting the H's fall off, we think of the H's one at a time. But if I'm reacting phosphoric acid with a strong base like sodium hydroxide, it'll rip those H's off, all right? It'll pull them off, all right? Don't worry about that right now. It's just I wanted to kind of clarify. There are a couple of situations where we do have to deal with it that way. Okay, don't write this down. I've got two examples here, and they really say the same thing. So I'm going to just talk about the first example, and then we'll actually do a calculation with the second example. So if you have your Ka sheet nearby, and we're going to be needing it today, so you might as well get it nearby, and being that it's so convenient, you can look at whichever side you would like. I don't even know if H2SO4 is on there. H2SO4, sulfuric acid, fulfills the requirement of a strong acid. There are there are two O's greater than the number of H's. Is it on there? It's got like times 10 to the 6 or something. 3? All right, I should get my copy, but you guys have it there. We're good. Times 10 to the 3, we consider that strong. So in this case, I just put up on my slide the Ka1 is very large. Can you find the bisulfate or hydrogen sulfate ion? I hope that's the same number. I think I got it from the same thing. You'll notice that the second H to leave is a lot weaker. And that is a true statement for all polyprotic acids. As you remove consecutive H's, the H's become weaker and weaker acids. They are not removed as readily, okay? So in this case, sulfuric acid, you put it in the water, all of them fall off, the first one. Pretty well every one of them. It's 10 times 10 to the 3. If we did a calculation, it would be like in the 90% range. Then you've got some bisulfate ion in the water, and a very few of these fall off, all right? The Ka2 is always less than the Ka1. Progressive hydrogens become weaker and weaker. Acids involved in each step of the multi-step ionization progress is progressively weaker because of the negative charge. It makes it less likely that the acid will give up the proton. Okay, so let's write down this next slide. So I had two examples there, but I think in terms of a note, you really only need one example, so not worth writing that first slide down. So in this case, we're dealing with phosphoric acid. It does not fulfill the requirement to be a strong acid. It does not contain twice the number of oxygens as hydrogens. So my first Ka, 7.1 times 10 to the minus 3. So it's fairly weak. A few of those H's fall off of the first molecule. And if we then think about what's happening to the dihydrogen phosphate, we can see there that the Ka2, 10 to the negative 8, getting weaker. A very small number of those H's fall off. And for that hydrogen phosphate, that last one to fall off, 10 to the negative 13. Very, very, very weak. Here we've got a description of the trend. The K3 is less than the K2, less than the K1. And so essentially when the question becomes, okay, how then am I going to determine the pH of the solution? Due to the fact that the second and third ionizable hydrogens are so weak, they will contribute such a small amount of H pluses. When it comes to significant digits, we can ignore them. The number of H pluses that are going to be contributed to the overall H3O plus concentration due to the second and third are so tiny that they're so far down in the list of significant digits that we can ignore them. So we only deal with the first Ka when we calculate a polyprotic acid. That simply, supports what I told you just kind of in general. Just deal with the first one falling off. Don't worry about the others. Now that's not to say we can't calculate things like the concentration of HPO4 minus in the solution. We actually can do that. We could even extend it down into the concentration of PO4 3 minus. We actually can calculate those concentrations. But when it comes to pH and that H3O plus, we are only worried about the first one, and we're only worried about Ka1. All right, let's do an example. Yes, Sean, it's different. I added part B, I think, is the new part. That's what I was going to trip over, but I had time to look at it. Now I know how to do it again. Okay, so we're dealing with the H3PO4. We want to determine the pH. As I stated on the previous slide, let's only worry about the first H falling off when determining the pH, which means oops, what's going on? Oh, why isn't that writing? That's new-ish. Oh, I see what's happening here. I don't have my, why did that not work? I want to be able to write it down because I'm making a movie here. So hold on one second, folks. Technical difficulties. All right. Okay, so as I stated, only deal with the first one. So if I want to determine the pH of H3PO4, all right, plus H2O to get H3O plus H2PO4 minus. And what was the Ka for that one? It's on the previous slide, but I didn't want to flip back. You guys have it there, right there. 7.5 times 10 to the negative 3. 7.5 times 10 to the negative 3. Is that correct? Is that good? Yeah? Good? Is it different than on the page? It should say on the page. Well, we'll go with what's on the page. It doesn't really matter. This is good. Must have came from a different page. Now, this is a weak acid. It's kind of one of those kind of weak acids. Question is, can I use the shortcut? We built this great shortcut in order to use it so we can answer these questions quickly. In this case, I have 1 molar, and there's my Ka. It's close. Is it going to be greater than 100? This is one where we should check the approximation to see if it's good. So I'm going to have, for the approximation, 1.00 divided by 7.5 times 10 to the minus 3. The reason why I'm looking at that is I know that the minus 3 is going to flip up to the top. It's going to make it 10 to the 3. That's in the thousands, but are we going to be in 500, or do these numbers mess me up? Is it going to bring me close enough? What's the value here? 133? Whew, that's pretty close. But it's 133, which means it is greater than 100, which means we can use our shortcut, which means we can go straight to the fact that our H3O plus is going to be equal to the root of Ka times HA initial. What did we say? The root of 7.5 times 10 to the minus 3, 100, and that's going to get me H3O plus. So now your approximation check is really a shortcut check, right? Can I use the shortcut? If you couldn't use the shortcut, you'd have a quadratic facing you down, because all acid ice tables will always result in the same structure because we always consider only one falling off. What do I have for H3O plus concentration there? And don't clear your calculators, because you'll just do a pH in a moment anyway. No one wants to give it up today? What is this? What's going on? Yeah, Shauna, what do you got? 8.7 times 10 to the negative 2 moles per liter, and therefore pH is, yep, 1.06? 1.06. Okay? We like that number? Okay. Now the second part of this question is, determine the concentration of the HPO4. Now you'll notice there is no HPO4 in this particular reaction, but in the second reaction where the second one falls off, all right, you will have an HPO4 in it. I'm going to clear the screen because I'm going to need a little more room in order to calculate this thing. But we are going to need to keep our idea of what the H3O plus concentration is. We also need one other bit of information. At the end of our ice table, we have X and X, right? Which means not only does this number give me the H3O plus concentration, but this number also gives me the H2PO4 minus concentration. It also tells me how much H2PO4 is in that solution. And that's going to become very important in determining the concentration of that next ion that's formed. So the H3O plus also tells me the H2PO4 concentration, because they're equal to X and X at the end of the ice table. All right? All I did was remind us that if this was the E line, I'd have X and X. That's the H3O plus, but that's also the H2PO4. Okay? Because when we look at the next part of this question, and I'm going to just clear the ink, we have to actually look at the second ionization. H2PO4 minus reacting with the water to produce H3O plus and HPO4 minus 2. And it also has a Ka. Now, we're not going to use this equation to determine the H3O plus concentration. I'm not worried about that because the H3O plus concentration is determined by the first H falling off because most of it falls off. I do need the Ka for my dihydrogen phosphate. Maybe we should go to the page because we went to the page for the last one. What do we have for dihydrogen phosphate as the Ka? Yep. Negative, and I missed that? 8? All right. Okay. We are not going to worry about looking for the H3O plus because it's going to be a very tiny number and we're not going to, it's going to be dominated by the H3O plus in the first one. But let's simply write the K expression. Ka is going to be equal to H3O plus, all right, times HPO4 minus 2 over H2PO4 minus 1. And I'm not doing an ice table. I'm not doing anything that complicated. I'm just writing the expression. Due to the fact that the first equilibrium dominates, we actually already know the H3O plus concentration and the H2PO4 minus concentration. That is equal to what was determined by the first equilibrium. The first equilibrium is dominating. It's loading the water up with H3O plus and H2PO4. What was that value from the previous part A, my previous slide? I cleared it away. What was that value, Elena? Times 10 to the negative, 2 moles per liter. Moles per liter. This is determined by equilibrium 1 as determined by Ka1 because it's dominating. What does that mean? It means due to the fact, or due to its dominance, I can put 8.7 times 10 to the minus 2 in for H3O plus because it's dominating. I can put 8.7 times 10 to the minus 2 in for H2PO4 because it's dominating that concentration as well. And due to the dominance of those two things, that will determine what the HPO4 concentration is in that solution. So I'm using the second K, Ka2, and then the concentrations from my first equilibrium to figure out what that concentration of that other ion is in the second equilibrium. The first equilibrium controls the position of the second equilibrium because the first equilibrium dominates. So now I just need to put in my numbers and rearrange. 6.2 times 10 to the negative 8. I'm going to have 8.7 times 10 to the negative 2. And this isn't supposed to work out this way, I don't think. It's gonna cancel out, isn't it? Does that cancel out? 8.7 times 10 to the negative 2. Well, that's interesting. That's mathematically giving me that. 6.2 times 10 to the negative 8. And that is equal to the HPO4 minus 2. And that's moles per liter. And to be honest, I don't know if that's true each time. If it's in pure water, I don't see why it wouldn't be true each time. Huh, is that a general statement? would that cancel out every time, and therefore the concentration of the HPO4 minus 2 is equal to the Ka2 every time? I'm not sure of that. I haven't done a question like this in a long time. That's what it seems to be presenting. We haven't done anything mathematically wrong. And the theory of the fact that the Ka1 dominates is the correct theory. I don't know if I would chalk that up to every time, but I don't see why it wouldn't be. If it's in pure water, we're going to have those exact values. I'm going to do some investigating as you guys are working later on in the class to see if that is truly the case. There could be even an ultra shortcut for that one, right? The concentration of that second ion would then be just equal to the Ka2. That might be the case. I don't see why it wouldn't be. That seems to be what it looks like. That's kind of neat. Wasn't expecting that result because I didn't actually do it ahead of time, which is the cardinal rule of not of bad teaching, but that's okay. Don't tell anybody. So there's a couple of questions that you can do dealing with that. Do we have all the information we want off that slide? So now I want to talk about weak bases. And the examples and the discussion for weak bases are exactly the same, but the base opposite of what we did for weak acids. The same possible shortcuts exist. The same possible shortcut equation, except in base terms, exists. All we got to do is check for approximations, and then we can then go ahead and do it. Weak bases tend to be molecular bases. They don't tend to be hydroxides, all right? So they tend to be molecules that have a high affinity for an H plus that can then pull an H plus off of a water molecule to produce a hydroxide and then the conjugate acid. It's not great at being a base, so its attraction for the H plus is kind of weak. That's what makes it a weak base. It doesn't pull on H's very well from the waters. Usually an amine, again, that's part of the organic chemistry course. We'll talk about that later. Non-metal anion, so we're talking about things like carbonates, sulfates would be good at grabbing up H's, maybe not great. Again, polyatomic anion. The non-metal anion could be fluorides, right? Fluoride is an example of the non-metal anion. That would be a pretty good base. Polyatomic ions, so things like a carbonate, CO3 minus 2. Those are weak bases. They react non-quantitatively. In other words, it's not 100%. So we need an equilibrium to describe it. And this is my short version equation. Just like we talked about having HA to represent any generic acid, we could represent any generic base just by a B. Then we have H2O, then we have OH, and I guess technically to balance out the charges, we'd call this maybe a B+, but I'm not that worried about it. If the base already had a negative charge, it would neutralize that charge. Now again, I'm going to have a slide examples of weak bases, and then we'll get into some calculations. But you guys are pretty bright. If the approximation is true, I end up with a situation that allows me to calculate the H3O plus from a weak acid's Ka using this equation. You guys are pretty bright. Let's flip this on its head. What's the shortcut equation do you think going to look like if we turn this completely into a base equivalent? What do you think, Christian? it's not going to be a Ka, right? Because we're not talking about acids anymore. So you're right, it's a Kb times the concentration of, no, it's not Hb. Hb is the conjugate acid, right? So it's not Hb. But close, nice try. What concentration am I looking for? Yep, just B, just the base, just the weak base, all right? Okay? So this here is the weak acid, it's the acid, and this, sorry, oh my goodness, this is the base, and this is the conjugate acid, all right? If I had the conjugate acid in the water, actually that would behave as an acid. I'd need this equation. But because I've got base in the water, I'm going to use that equation. Don't worry about writing this down. The ionization constant for weak bases. It's the exact same slide as the other day. It's called the base ionization constant. It's called the Kb. The bigger the Kb, the stronger the base. It's exactly the same, but it's flipped over on its, on its, not its head, but its base equivalent. Let's do a quick little shortcut here. And I actually wanted to, I'll just get rid of that example down at the bottom because I want to just, I want to derive the shortcut just to show you, so I'm going to just delete that example away. So if we're dealing with a generic base, again, because it's in pure water, I'm dealing with some initial concentration of B 0, 0, it's in pure water, minus X, 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 initial concentration of B minus X, 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 Kb, just to do it officially, is OH minus times Hb, which is the conjugate acid, over the concentration of B. If I substitute everything in, I'm getting an X squared over the initial concentration of B minus X. That's equal to Kb. If the approximation is no good, we've got to crash through that, and we've got a quadratic. If the approximation is good, I can get rid of that X there. Kb is equal to X squared over the initial concentration of B. Bring that up to the other side, take the square root, and, oops, that's not H3O plus, OH minus is equal to the root of Kb times the initial concentration of B, if the approximation is good. Again, X is the OH concentration. We now can then take the negative log, get the POH, minus 14, get the pH, and crash through again. And again, if the approximation is no good, we need to keep that equation there and do a quadratic to solve it. So really nothing new here, except we're dealing with OHs today, and we're gonna have to subtract from 14 to get the pH. Okay, so now just some examples. For some reason, there is no percent ionization equivalent for bases. At least I don't think there is. Did I change this up and have some of those put on there? I don't think so. Let's see. Boom. Yeah. Nope. Ten to the minus 6, 0.1. That minus 6 is going to come up to the top. It's going to become 10 to the 6th. That's a 10 to the negative 1. That's going to be 10 to the 5th, right? So definitely a shortcut. I put that question on there, and I'm likely giving you 3 marks for it, maybe 4 marks, a couple of marks for finding the OH, a mark for determining the POH, a mark for subtracting from 14 and determining the pH, right? If I put on there something like 8 marks, and this KB is like 10 to the minus 2, then there's a little hint you can't use the shortcut, because I'm going to need to see an ice table and I'm going to need to see a quadratic equation, right? We kind of got busted on that one on the common ion effect problem, where I think it was out of 6, and many of us just did the shortcut equation. You probably maybe were not sure on what to do, so you put something down, which is a good thing to do. But you look at those marks and you think, whoa, just putting an equation down and putting numbers in it, something's not right. In this case, we can use the shortcut. OH. We just wrote this equation down. KB 1.7 times 10 to the minus 6. I'm not going to rewrite the equation. 0.100. Then from that, POH, pH, and this should become, right, very systematic for you guys. Don't clear the calculator out of the POH. Write the number down. Negative log or negative log answer for those of us with superior calculators that work in reverse. Just press log and then ignore the negative. And then 14 minus answer equals, or whatever you do. And so dealing with a weak base is not a scary thing. If the approximation is good, you can get the pH just like that. I'll take all 3 numbers if somebody has them. Sorry, negative 4. Negative 4 moles per liter. Got to have the units on that. It's going to be 3 point something. Sorry. 3.3. 3.38 and 10.6. I guess we should have had an extra decimal. Doesn't. 6.2. 6.2. Okay. All right. Yeah, I should have been able to figure that. We're getting good with the calculators, right? Sarah didn't even bother writing down POH because all you got to do is 14 minus answer equals, right? On the test, I guess I'm not concerned, but if you do a screw up in there and I can't give you the part mark in the middle, you know, it's kind of like gambling, right? You're going to leave out that step and you make a mistake from here to here, then I got to take 2 away. You show me that step and you somehow screw up 14 minus. I don't know how you do it, but you do, right? Then I only take 1 away. You see how the way that works? You know, the less data you put down, the more risk of not getting part marks you run. What's the good question? I heard a good question. I like good questions. Did you say good question? Oh, read the question. Yeah, read the question. Come on. I don't like those questions. So this is that opposite scenario, right? We want to figure out what the KB is. You could memorize that little equation with the square in it, but I would just memorize this, right? Once you've got the one memorized, you've got the other memorized, and then all you got to do is rearrange and solve. Oops, that's a B. Square both sides, divide by the B. Again, how much information you want to display to me depends on, you know, your gambling tendencies, I guess. Did I just say that? Your gambling tendencies. If you want to write down, right, POH equals, that might not be a bad move because sometimes we might forget to do that, 14 minus 9.94, because we do need that POH value, What is that? That's 4.06? 4.06? 4.06. And if you want to actually calculate the OH and show me, again, that's a good thing to do, 10 to the negative 4.06. But if you want to just put that 10 to the negative 4.06 into the calculator, it should be able to handle that 0.0100 equals KB. That's up to you, all right? If I were to see that set of logic right there, then I wouldn't penalize you for necessarily not writing down the number for, you know what I mean, for OH minus. That is the number for OH minus. It's just not expressed in scientific notation. So left bracket, you could probably do second function log to bring that 10 to the x up, or you could do left bracket 10, arrow up, negative 4 point whatever, right bracket squared. For those of you with the archaic calculators, you've got to do multiple steps in there to make it work, but hey, whatever you got to do. What do we have for a KB there? Yeah, what do you got, Tina? Times 10 to the negative 7? I think you said 5/6. Is that what I caught? All right. And if we do a quick check, that's quite small. Our approximation would have been fine. We can stay with that. If we get a number that's close to this number, we really should go through the ICE table, keep that extra x, and dump it into the K expression to get the KB. Oh, and this one, excellent. And then this is the last one. This one I throw in because this is technically example of a weak base, but it has nothing to do with what we did today. It has everything to do with dissolving of a solid that isn't very soluble, because that can also be a base if it's an insoluble hydroxide. So in this case, what do we have? We have some magnesium hydroxide that is dissolved in water. It's made a saturated solution of magnesium hydroxide. This goes back to our dissolving of solids situation. This, again, also is, we've got to assume here that it's pure water, because it doesn't say anything about a common ion effect scenario. That would be mean. You could do it. I could say, what's the pH of a what do we got here? Determine the pH of a, it just says a solution. That's mean. I could say determine the pH of a saturated solution of MgOH in magnesium, in 0.1 molar magnesium chloride. That would just be mean. That would be a common ion effect problem where then in the end you got to figure out the OHs, et cetera, et cetera. Anyway, here's what we've got to do. We've got to determine the OH concentration. Because this is a solubility, and because the KSP is really small, we can solve this problem by the fact that this is an MX2, right? And if it's an MX2, we might be able to remember what that X equation is for the solubility, how well it dissolves. Does anybody remember what it has to be? Anybody? Sarah, what do you got? Third root of KSP over 4. Fabulous. That's exactly correct, right? Because we've got the 3 ions, which means it's going to be a cubed root, and then we've got that 4 because we had to square the 2. All right, well, let's go ahead and do that. 3, and that's 5.6 times 10 to the minus 12, and that's over 4, and that's equal to S. And remember, that's the molar solubility. It's not the H3O plus or the OH in this case. This is the amount of stuff that can dissolve. Lots of X's here in this business. What do I get for the solubility of the magnesium hydroxide? Taking a cubed root, I'm going to take that negative 12 and divide it by 3, so we're looking at the negative 4 area. Yeah, Kristen, what do you got? And 10 to the negative 4, was it 4? 10 to the negative 4? Negative 4. And that's moles per liter. And that's moles per liter of MgOH 2 that can dissolve. So that many moles of MgOH2 broke apart. Therefore, what's the OH concentration? If 1.12 times 10 to the minus 4 moles of MgOH2 dissolved, how much OH is there? Yep, Kristen? I doubled it, right? It's that 2 OHs for each MgOH2 that dissolves. So it is 1.12 times 10 to the negative 4, and this is like the 2-to-1 ratio scenario, right? 2 to 1, 2 OHs to 1 magnesium hydroxide. That's like the hypothesis question in our little experiment that you got back, right? We had to double to get the OHs. So in this case, the OHs, and I think I can do that. What's that, 2.24? In this case, the OHs come from a dissolving solid. That's a completely different question that deals with what we dealt with before, but still, it will result in a pH change. So now I can get a POH and a pH. Hopefully it's just a matter of straightforward doing that. And I'll just take the pH on this one. I trust you that you can then do 14 minus whatever. Now, you're not going to have one of these in your homework questions because the ones I'm giving you are just dealing with the molecular bases. But that's a fair game question. That's an exam type question because it brings two concepts together. Oh, I got to do solubility, and then, yeah, it's terrible when we bring two concepts together. Isn't it crazy? All right. Do we have a pH value for this? Yep. 10.35. 10.35. All right. So this was an example of a low solubility hydroxide. If I had simply sodium hydroxide, I'd need to know what the concentration is, and I would need to then just take off the H or OHs. That's 1-to-1, right? They all fall off. But in this case, I need to do a solubility problem in order to determine the OHs. All right, and that's the end of that. And there are some practice problems with that. And I am done for today. You got time to work.